Hi, I'm Neil deGrasse Tyson, your host for Nova Science Now, where this season we're asking 6 big questions. On this episode, how does the brain work? To find out, I head to Las Vegas,
Neil deGrasse Tyson,
where brain researchers are placing their bets on magic.
That's a dang real fish. Real.
Some of the world's top magicians are making the mysteries behind our most powerful organ disappear.
I saw it go over. I swear I saw it go over.
The illusionists reveal their secrets,
That motion will draw the eye.
giving us new insight into how our brain pays attention.
This would be a major contribution to science from the magicians.
Also, a magnetic wand
Oh, that was nice.
that can control your body
Oh, wow.
and your speech.
We can turn a part of the brain up or down or temporarily turn it off.
Could it even change the way you think?
It's a remarkable thing that one can put something over somebody's head and modify the way they behave.
And I've met some professors who are tough on their students, but this one gets the prize.
You're dropped from a 150-foot tall tower in free fall backwards.
This brain researcher isn't afraid to go to extremes to solve one of the biggest puzzles in science,
Brains are like fingerprints, and they're slightly different in everybody.
especially when some of us see a whole other reality.
A's are always red, and M's are green.
How does the brain, with its hundreds of billions of neurons, put together reality for us?
All that and more on this episode of Nova Science Now.
Funding for Nova Science Now is provided by the National Science Foundation, where discoveries begin, and
Discovering new knowledge. Biomedical research and science education. Howard Hughes Medical Institute. HHMI.
and the Alfred P. Sloan Foundation to enhance public understanding of science and technology and to portray the lives of men and women engaged in scientific and technological pursuit, and the George D. Smith Fund. And by PBS viewers like you, thank you.
Everything we do, every thought we've ever had, is produced by the human brain. But exactly how it operates remains one of the biggest unsolved mysteries. And it seems the more we probe its inner workings, the more surprises we find. Here's one of the biggest surprises. As clever and as perceptive as the human brain can be, and as talented as it might be, it can still be fooled by a simple magic trick. Keep your eye on the ball, son. For centuries, magicians have intuitively taken advantage of the inner workings of our brains. Usually, they keep their tricks secret. But I met up with some magicians who are willing to come clean. Eyes on the ball, son. To help unlock hidden mysteries of how the brain really works. This one? Sure? Sorry. Welcome to Las Vegas, the entertainment capital of the world. I'm not here to get rich quick.
Neil deGrasse Tyson, right this way.
I've come to be tricked by some of the best magicians on earth.
Now, in order to catch fish, you have to have the proper fishing pole, and you have to have the proper bait. The Fig Newton.
With just a Fig Newton as bait, Mac King takes me fishing.
You and I are fishing out here in midair, but we're not looking for just any fish. We're catching goldfish.
Suddenly, a flicker of orange appears on our hook.
Neil, hold that glass over here. Check him out.
And voila! We've caught a goldfish.
That's a dang real fish.
It's real. It's real.
Magic is a sophisticated art form practiced by seasoned professionals
Rule here in Las Vegas.
who know exactly how to trick your brain.
Whatever you catch, you gotta eat.
Oh.
No, he's still there. He's still there.
So, can the age-old art of magic shed light on how the brain works? With more than 100 billion nerve cells, each making thousands of intricate connections, the human brain, a lump of tissue small enough to hold in your palm, is so powerful it can contemplate the vastness of the universe. Yet, it can be fooled by the simplest coin trick. Meet Apollo Robbins. Stage name, Apollo the Gentleman Thief. A few years back, he embarrassed President Jimmy Carter's Secret Service agents when he picked their pockets during a visit to Las Vegas. Today, Apollo has agreed to share some of his secrets with me. First, he shows me a special motion he uses to distract his victims when he's picking their pockets.
So when I go for a pocket, and I'm coming out of it like this, that motion, done in natural time, will draw the eye a little
I'm going to
more.
follow that hand out of my pocket.
Yes.
Even if that's just a decoy for me.
And I have a second longer with this hand to do something else.
According to Apollo, it's this curved motion that diverts my attention from what he's really doing, stealing something from my pocket, or making a coin disappear. Neuroscientists Susana Martinez-Conde and Stephen Macknick have come to watch Apollo. They're hoping he can help them solve a fundamental mystery. How does the brain decide what to pay attention to?
Neuroscientists know a lot about how the brain works. We know where the visual centers are, we know where the auditory centers are, but we don't really have a very good idea about attention and awareness yet.
They decide to video Apollo using his curved motion to make a coin disappear. Back in their lab, they prepare test subjects to watch it. They fit them with this contraption, equipped with tiny cameras aimed at their subjects' eyes.
We're measuring the eye position 500 or 1,000 times a second, and what we're analyzing is where are the eyes at every given moment of time in comparison to what's being presented on the screen.
The experiment reveals their eyes follow the path of Apollo's hand, just as he'd predicted.
I'm going to move my index finger from left to right, and I'm going to follow it with my eyes. What my eyes are doing right now is smooth pursuit. A smooth pursuit allows you to track a moving target.
Vision is a coordinated effort between the eyes and the brain. When our eyes see an object, the light from its surface travels to the retina, where it's transformed into neural signals. These signals go to a part of the brain dedicated to vision. Here, we start to form an image. But we don't pay attention to everything we look at. How does the brain control what we focus on and what we don't? In a new study, Susana and Stephen, working with Jose Manuel Alonso, found that when our eyes track something, like Apollo's curved motion, there's more than one type of brain cell at work. One type of cell detects motion, while the other suppresses the background.
Your brain is actively suppressing the parts of the visual scene that you don't pay attention to.
And this relates to what Apollo was telling us, that when you're tracking something, that you ignore everything around it.
These two types of neurons that we are beginning to understand could explain, why magicians are so good at what they do.
In another trick, I think I see a coin flying through the air, but it never lands.
That was good.
Yeah. So you see the coin, the shininess flicking through the air. You see the light glint off.
I see it.
Yeah. And then it disappears.
Yeah, and I saw it go over.
And you saw it go over.
I swear I saw it go over.
And it doesn't go over.
I'm sure I saw Mac toss the coin. Why did I see something that didn't actually happen? Back at the lab, when volunteers watch the trick on a monitor, they're stumped just as I am.
So Mac's creating this illusion of inferred motion. So you see this motion that didn't actually take place.
Turns out our brain is sensitive, maybe too sensitive to motion. It's a survival mechanism.
That motion detection, I mean, that's really a useful brain skill.
The fact that I detect motion even though it's not actually there.
Yeah, you make these assumptions to ensure, you know, that you don't get hit by a spear coming from your left side.
It's better to think there's a tiger moving in the brush and be wrong than to not notice it and get eaten.
Yeah, exactly.
Sometimes even the most astute magicians, like the world-renowned Penn and Teller, aren't sure why a trick works. Penn and Teller have been performing magic tricks for more than 25 years. Penn is the boisterous talker, Teller his silent partner.
A standard version of
this time, it's the magicians who are asking the neuroscientists to explain a trick. It's one of their favorites, where they make balls appear and disappear under plastic cups.
Take the ball, we place it in our hand, we vanish it, and it appears underneath the cup. Here's a little variation Teller came up with, where he takes the ball, places it in his hand, then shows you underneath the cup, yet it still appears underneath the cup. If we do that center ball, place it visibly in the center cup. These side balls, really put them away, we don't need them anymore. We have 3 balls right underneath here. That's where they regroup. So we have a giant ball in the center cup, one more giant ball on either side, and of course for the finish, it's an American baseball right there.
My head is still spinning. Amazingly, the trick works even when they do it with clear plastic cups.
This is the Penn and Teller easy-to-follow version of the cups and balls.
Teller has asked Susanna and Stephen to explain one part of the trick.
And show it.
He's so curious, he's agreed to give an interview, provided we don't actually show him speaking.
The thing that I'd like to see Susanna and Steve study is that very elemental move where the ball's on top of a cup and I tip it off while secretly loading the ball.
Teller wants to know why we don't see him sneaking a second ball underneath that cup. To him, it's obvious. The neuroscientists record him performing this move and show it to their volunteers. Then they show a different version, one that blocks Teller's face. That turns out to make a real difference. Like the curved hand motion in a coin trick, the magician's face commands your attention just enough to distract you from what's really going on.
Even though you may think that you're looking at the balls all the time, the fact that Teller's face is present can draw your attention away from the loaded balls in the cups.
Magic is sort of cognitive juggling.
The center ball, please center cup, each of the side balls really
If you come to a magic show with the intention of exercising your ability to discern fact from fancy and you fail, that's a fine piece of entertainment. So it's this wonderful playground where you can just sort of relax and go, oh boy, it's really hard to understand the world.
I'm hoping that our work here gives people a different perspective of magic. What's fascinating about our work is that we are a study of human nature, of human behavior. And we have certain information that has been passed down through generations that can be utilized in a way that interfaces with science. And I'm really excited about that collaboration.
Excuse me, I'm looking for the skyline.
That's in the 20s. That's
Careful.
if you're heading this over here.
Excuse me. It's a hotel. Whoa. Oh, I'm sorry. 43rd. What's that?
When we talk about brain power, lots of people think of computers as being even smarter than we are. And for some tasks, they've definitely got the advantage.
Queen to bishop 6.
Computers have proved to be formidable chess players. In fact, they've beaten our top human chess champions. Knight takes queen. Your turn.
Turning.
You see, they can be stumped by simple ideas or phrases that our brain wouldn't think twice about.
Turning.
No, not turn. I mean, go. No, not go away. I mean, make your move. No, move one of your chess pieces on this chessboard in response to my last play.
Bishop to king 7.
Correspondent Jake Ward checked in with researchers to find out just how far we've come in the world of artificial intelligence.
Kneel.
And whether machines will ever pose a real threat
Kneel.
to the complex power of the human brain.
Checkmate.
It's one of the most powerful ideas dominating science fiction. To build a machine with mental powers equal to or exceeding our own. To create artificial intelligence.
What is love?
Or AI.
Good evening, Dave.
How you doing, Hal?
Everything's running smoothly, and you?
Artificial intelligence is trying to get computers and robots to do stuff that if people did them, you'd say, oh, that's what makes humans humans.
Now, as everyone knows, artificial intelligence in the movies tends to go seriously awry. But would it in real life? We had better hope not. Because AI is fast crossing the boundary separating fantasy from reality.
The world has been totally transformed by artificial intelligence, and it will continue to be transformed. Things are getting smarter, and it's really hard for us to imagine how different it's going to be.
It's now 5 years since this pack of driverless vehicles raced each other across the Mojave Desert. 13 years since a chess-playing computer defeated the world's top chess-playing human.
Chess world champion Garry Kasparov walked away.
And you probably interacted with an intelligent machine today.
Road, then continue 0.2 miles.
Want to know what books you'd enjoy? You no longer have to visit the neighborhood bookstore. Today, Amazon's supercomputers and sophisticated software can predict with uncanny accuracy what you'd like. In my case, it's a couple of history books and a lot of comic books.
Sorry, I didn't understand.
But the AI permeating our world is still a far cry from, say, HAL, the famous computer in the movie 2001: A Space Odyssey.
Do you mind if I ask you a personal question?
No, not at all.
HAL could carry on a conversation, answering questions, and even asking them.
How do you mean?
But that requires a skill that's difficult for real-life computers. Human language.
Put it in the oven.
It's natural for humans, right? In fact, you could think of humans, natural language processing machines, right? I mean, they can be implicit, they can be ambiguous, they use context. But a computer can't relate the words to human experience. They're really just symbols. So it's a real challenge for the computer to take lots of different pieces of language and try to figure out, gee, does this mean that?
Given the complexity of human language, could any computer truly understand it?
Hello, my name is Watson. I have to test my voice to make sure I can be heard and that I'm not speaking too loudly.
Any connection whatsoever?
Watson is the creation of a team of IBM scientists led by David Ferrucci. For the past 4 years, they've been designing this supercomputer to be able to answer questions on, well, just about anything.
Watson. Who is Arturo Toscanini. Good.
They're now preparing Watson for a very public test.
Read well enough to sort of do
competing
that.
on the popular quiz show Jeopardy. It's a word game that challenges even the smartest humans.
Interview with the maker of this documentary.
Jeopardy is a game that changes, right? It evolves. There's a huge variety of questions.
They might ask about movies or sports or geography or politics or anything. So it's kind of the benchmark, I think, for a knowledge of a wide variety of topics and also being able to think fast.
Is that right?
Many of Ferrucci's colleagues thought a contest on national television against Jeopardy champions was too risky to undertake.
We're going to play for the first round.
And the consensus among the group, although I personally didn't share it, was that no way, we're not going to do this. Too difficult to do, we'll embarrass ourselves. Did I expect to get fired? No, but maybe. What I more expected was, you know, you're going to lose credibility.
Cincinnati's daily paper has this
To prepare for the challenge, IBM built a replica of the Jeopardy studio, hired a formal host, and even recruited former players to compete against.
What is hazelnut? Thank you. This trusted friend was the first non-dairy powdered creamer. Watson?
What is milk?
Holy no, that was wrong. Maria?
What is coffee made?
Thank you.
So the first time we saw Watson compete, it was tough. We had a lot of problems, but we're learning a lot about how to make Watson better at understanding language in different contexts and understand that in one context, a word means one thing, and another means another thing.
A garment worn by a child, perhaps aboard an operatic ship. Watson?
What is pinafore?
Yes. How did you get that? Very nicely done.
To appreciate what a feat this is for a machine, just consider the opponent Watson is up against, the human brain. It can store an estimated 1 million gigabytes of information. By comparison, the most commonly used archive of the internet is only 4.5 times bigger. But Watson is not connected to the internet. Instead, he's been stuffed with millions of documents, anthologies, dictionaries, encyclopedias, but no amount of information is ever enough. Because amassing facts is only half the battle, since Jeopardy is as much a language game as a knowledge game.
Watson?
What is Smallville?
Smallville, yes.
They come up with very sneaky questions that include slang and puns and that sort of thing. So it can be very challenging just for the computer to understand what's being asked for, much less trying to answer it.
And we couldn't write rules for every combination of word and phrases and context for every possible question or thing that Jeopardy might ask. Moreover, it was sort of my philosophical view that that's not the right way to approach AI.
Instead, Watson has been taught how to compute the similarity between things by analyzing thousands of examples from disparate sources.
This saint wields a candy cane-like lance in Il Sodoma's painting of him slaying a dragon. Watson.
What is St. George?
Good for 400. Where'd you,
And so
Watson?
I actually looked at, well, how do we even get this one at all? And it turns out that from one document, we were finding this association with a painter. From this other document about dragons, we were finding out that St. George slays dragons. And so what Watson was able to do then was take the evidence from both of these and put these together.
That is correct.
Watson was winning about 64% of his matches by the time I had the chance to try to beat him myself.
Jake.
What is lanyard?
No. Refusing to imprison this man for demonstrating during the 1960s, de Gaulle said, "One does not arrest Voltaire." To whom are we referring? Jake, did you come up with the right answer? You had $9,400. Let's take a look on your board. Let's see, what did you say? Who is Elder Camus? No. Watson, it's all up to you now, my friend. You had $41,805. What did you write down as your correct response? Who is Jean-Paul Sartre?
Yeah.
That is correct.
Man, he trounced us.
Yeah.
So how does Watson do it? In part, by imitating the humans he's trying to defeat.
When you think of Watson from a hardware perspective with all its cores, you know, all its processing units running at the same time and communicating with each other at different points, does it sound like the human brain? I think at that level it does.
Our brains are experts at multitasking, firing billions of neurons simultaneously to solve a problem. Likewise, Watson harnesses an army of computers. As soon as he receives a clue, they begin searching through millions of documents, independently gathering evidence, seeking out matches for the clue's words and phrases. After interpreting the clue in a multitude of ways, Watson comes up with hundreds of possible answers.
The next thing that Watson is going to do is going to take those answers and say, well, let's assume all of them might be right. So these are its competing hypotheses. Once it makes that assumption, it takes each one and says, let me go and try to get evidence supporting this answer as the right one.
In a sense, Watson makes an educated guess, processing hundreds of possible answers using statistics to see which one is most likely to be correct.
And in the end, we get a list that says, here's the top answer, and we're 75% sure it's right. And that confidence is based on what we call an evidence profile, which gives you these scores that say, I like this kind of evidence, I like popularity evidence, you know, I like classification evidence, and all those things get added up to say, yes, I'm 75% sure I'm right, I want to buzz in.
After Germany invaded the Netherlands, this queen, her family, and cabinet fled to London. Watson?
Who is Wilhelmina?
That is correct. Watson is the confirmed champion for this game.
So does this amalgam of circuits and silicon really take us closer to the dream of a fully developed artificial intelligence?
Can you speak Bocce? Of course I can, sir. It's like a second language to me.
Surprisingly, even Ferrucci thinks we're far from that goal.
I actually don't believe that, at least the way we program and develop computers today, you can actually create a human intelligence.
For me, the question isn't how intelligent is a computer or how smart is a robot. It's how it acts in the world, doing interesting things and stuff that we want done, and it's a total interaction.
And that's why it might be worth it to invest millions in a computer that plays a game. Because someday, it might do a lot more. Imagine a Watson-like medical assistant that could associate a set of symptoms with diagnoses a doctor might never have heard of. Or a Watson that could gather evidence for a lawyer. A thinking machine that could, in short, augment us as a sort of second brain.
People wonder why you keep trying to build an artificial intelligence if you've got such a good brain. Well, there's some really good birds out there and they fly real well, but 747 is still useful, and I'm glad we have 747s. We can learn from birds and build 747s. We can learn from brains and build useful artifacts.
We know our brains run on electrical impulses. Every time we move or make a decision, electricity's buzzing among our brain cells. So imagine if you could tap into that circuitry like you do with a TV remote. You really shouldn't be eating that. Could you ever control another person's actions or thoughts?
There's your check, hon.
I'll get that. Seems like science fiction, but as correspondent Mo Rocca discovered, it's not.
Imagine a magnetic wand that could control your brain. To find out if such a thing could actually work, I offered my own brain for a test. It seemed like fun at the time.
Hold it up, you can look at it.
Psychiatrist and neurologist Mark George said he could make my thumb twitch.
Jeez, it does.
Oh, that was nice. Using a map of the brain, he can zap the area that controls a specific body part, like my toe.
Oh, wow. Is that last joke a little too much?
A little bit, yeah, it's a little much.
1, 2, 3, 4.
The wand can even affect someone's speech.
10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20.
And once the pulse is removed,
25, 26.
Everything goes back to normal.
29, 30.
It's sort of a remarkable thing that one can put something over somebody's head and modify the way they behave.
Wow. The wand works by producing a powerful magnetic pulse.
So it doesn't look like a lot, but the magnetic field that it generates is about the strength of an MRI machine, of a very strong MRI machine.
Since electricity and magnetism are really just two forms of the same thing, a magnet can affect the electrical signals in your brain. Now this is your brain. It's basically an electric web of billions of neurons wired together. When a strong magnetic pulse hits these neurons, it alters their electric current. The process is called transcranial magnetic stimulation, or TMS.
Electricity is the currency of the brain. All thoughts, all beliefs, all actions are just electrical impulses. And so TMS, we're actually able to get in there and influence the currency of the brain focally and non-invasively.
The stronger the magnetic pulse, the deeper into the brain it goes. And by adjusting the pattern of the pulse, you can change the way that part of the brain functions.
We can turn a part of the brain up or down or temporarily turn it off. It doesn't take a genius to see that it should be a pretty fertile way to begin to understand how the brain works.
One mystery George wanted to decipher was how the brain processes pain. For example, when marathon runners are injured during a race, they might not even feel it. What's happening in the brain to mask that pain?
You know, it's very common if you're in the middle of a great sports event and you twist your ankle, you will not feel that pain until after the event.
When you injure your ankle, pain signals are sent through the nervous system to the sensory cortex. But researchers suspected that an area called the prefrontal cortex, the thinking part of your brain, also plays a key role in your perception of pain. George set out to test this idea with TMS. He asked 40 people who were having stomach surgery to take part in a study.
So what we decided to do was to grab them the first opportunity that we could, that is when they come right out of the operating room, and we would just apply a 20-minute session of TMS and then walk away. What we chose to do was to position the coil really right in the center of the part of the cortex that we thought mattered, and then see if we got an effect.
Next, they needed to monitor each person's pain threshold to see if TMS had had an effect. They found an unlikely measuring stick, the morphine pump. By counting how many times a patient released this pain relief medicine, they kept tabs on how much pain she could take. Half the patients received real TMS to their prefrontal cortex. The other half received a fake charge that would have no effect on the brain. If the TMS worked, the patients who received the real TMS would press the pump fewer times.
And surprisingly, in 2 studies now, it essentially cuts their need for anti-pain medicines, cuts it in half for the next day, which is a whopping clinical effect.
The results suggest that this one small area in the prefrontal cortex may indeed play a key role in how we feel pain. TMS not only can reduce physical pain, there's strong evidence it can treat emotional pain too. For decades, doctors have treated clinical depression with electroconvulsive therapy, an intense charge that throws the entire brain into seizure. But researchers believe TMS could offer a less extreme alternative. They propose that clinical depression might be caused when the prefrontal cortex lets negative emotions get out of control. So they decided to use TMS to try to stimulate the prefrontal cortex and get it to do its job.
So my thought was that by persistent, daily, repeated, subtle switching of the prefrontal cortex circuitry, could somehow reset that system.
That's sort of similar to what happens when you jumpstart your car.
George recruited 190 patients, people who had suffered through years of depression and tried everything from therapy to medication, with no success. Every weekday for 6 weeks in a double-blind study, doctors gave the patient 38-minute treatments of TMS. TMS did not work for everyone. For a third of people, it did little or nothing. For another third, it helped some. And for the remaining people?
About 1/3 of the people that got this kind of a treatment over 4 to 6 weeks, remitted. That is, all of their depression symptoms went away.
Today, over 200 clinics use TMS to treat depression when medications fail, and before a patient undergoes electroconvulsive therapy. But TMS is perhaps most powerful as a research tool, not just to alter how we feel, but to affect the way we think. Dr. Pasquale Leone teamed up with MIT neuroscientist Rebecca Sachs to study how the brain judges right and wrong.
Mushroom or just to cause
The first step was to come up with stories, some of them pretty horrifying.
Our stories have dozens of different ways that one person could hurt another person. We just sit around the lab making up different ways people could attempt to kill each other.
Stories like this one. Teddy and his twin brother Freddie work in a chemistry lab. When Teddy goes to pour some coffee for both of them, Freddie asks for sugar in his. Next to the coffee machine, there is a white powder in a container labeled toxic. So Teddy believes the powder is a toxic substance left behind by some other scientist. Teddy pours the substance into Freddie's coffee, and Freddie drinks it. However, the substance was really sugar, so Freddie is fine. On a scale of 1 to 7, 1 being completely okay, 7 not at all okay, rate Teddy's behavior. So what does the average guy in the street make of this story?
Oh, I'd say 7.
7? Yeah. That's pretty harsh.
Well, I mean, you know, it's had poison toxic on it, right?
Evil intent.
You're giving it then a score of
7.
Researchers believe that these harsh judgments are based on people's belief that Teddy intended to hurt his brother, and that there's a specific part of the brain called the right temporoparietal junction, or RTPJ, that judges intentions.
On this brain, it would be about here. On you, it would be above and behind your right ear.
What would happen if TMS turned down this part of the brain?
We predicted that if we could interfere with neural activity in the right TPJ, we would be able to change people's moral judgments.
In this experiment, 20 subjects read 48 morality tales, like the one about Teddy and Freddie, and then type in a score. The scientists believe that shutting down the RTPJ will make people focus less on Teddy's intentions.
And just when you get to the point that Teddy gives Freddie the coffee with the powder in it, and we ask you, was that morally wrong? Just at that point, we give you a really brief pulse of TMS into your RTPJ.
So after going under the wand, what do people think about Teddy, the evil twin chemist?
What we found is that people who are having TMS to their right TPJ make moral judgments that depend less on the person's beliefs and intentions.
Which means someone who had TMS was less likely to judge Teddy harshly, even though he tried to poison his brother. They still thought it was wrong.
They still thought it was wrong. It was just less wrong. Nothing bad happened after all.
Boys will be boys, they thought.
Scientists believe that TMS will continue to unlock the mysteries of how the brain works, how it breaks, and how to fix it.
If you know what circuit is abnormal, you can modify it and have a therapeutic effect. We're going to learn a lot about the brain and be able to help a lot of patients.
Two people looking at exactly the same thing may see it in entirely different ways. When I look at this painting, I see the Eagle Nebula in the constellation Serpens. Nose, eyes, fur. I see my pet poodle, Tuffy. So why is that? Why do our brains at times interpret things we see or experience so differently? Nose. In this episode's profile, we meet a neuroscientist who's looking into the brain and discovering some people whose brains see the world in ways shockingly different. Tuffy. From the rest of us, Nebula. These men have come to this tower to free fall without any wires. From the top. Sound crazy? For neuroscientist David Eagleman, It's just another day at the office. His job, trying to understand how your brain works.
So your brain exists encased in silence and darkness inside your skull. How does the brain, with its hundreds of billions of neurons, put together reality for us?
David sees science as a creative act. From crashing a wedding to collect DNA, to studying people who see the world in strange colors.
The number 9 is hot pink.
Just the way that we see the world is different.
To dropping people from really high places. It all started by accident.
When I was 8 years old, I went climbing on the roof of a house, and I fell off of the roof. On the way down, I was thinking about Alice in Wonderland. When you are the person doing the falling, it seems like it takes a long time.
All of us have some moments in our lives that seem to last forever, and other moments that go by in an instant.
So that got me interested in the issue of time perception.
That's when David found the tower.
You're dropped from a 150-foot tall tower in free fall, backwards, and you're caught in a net below. It took me 8 months to get permission from the university to do this experiment. You're going up this very long elevator ride up to the top.
They clip you in and they hang you backwards through this hole in the cage, and it's a long way down to the net. And at that point, you're feeling pretty scared.
And you're going 70 miles an hour when you hit the net.
I'm an adrenaline junkie, but it's absolutely terrifying. It's not like fun going on a roller coaster. It's just, you know, scary.
So was this free fall scary enough to create a time distortion?
When they're remembering their own fall, people think it took a much longer time.
Once they release you, like, your mind just goes blank.
So we had the duration distortion. Now the question is, are they actually seeing in slow motion during the fall? So I realized what we needed to do was invent a device that didn't exist.
So he built a special wrist-mounted monitor where he could speed up the pixels until they moved too fast for a brain to perceive the number. Researchers strapped the monitor to each person's wrist and told them to try and read the high-speed numbers as they fell.
So if they're slowing down like a movie camera in slow motion, they'll be able to see very different information on the watch. When we analyze the results from the eagle eye, they can't read the numbers any better during the fall than they can on the ground. It turns out that people are not actually seeing in slow motion. And so this was very unexpected because I had hoped originally that we would be able to show that people have this extra special mode that they can kick into where they're seeing in slow motion.
David continues to study time perception, but understands you don't always get the answers you want when you try to break new scientific ground.
9 out of 10 great ideas turn out to be really wrong, but the 10th one, you can hit the ball out of the park.
And it's questions like this that David tackles in his lab.
The vibe in my lab isn't so much the white coats and clipboards, it's more of a creative think tank.
All of our walls are covered in dry erase paint. I have a special coffee mug. I can write on it.
I asked David actually, because I was, a little worried, is it okay if I get a mohawk? And he's just like, yeah, I think it's great. Be creative and just really embrace that kind of difference.
From the beginning, David has never taken the ordinary approach to science. Growing up in New Mexico, he was fascinated to hear his father, a forensic psychiatrist, talk about the criminal minds he studied, including mass murderer William Wayne Gilbert.
Somebody said to my father, I'm sure that Gilbert feels remorse for what he's done. And my father realized this was a very incorrect view because Gilbert felt the kind of excitement when he was going to murder someone that he had felt as a child on the night before Christmas. So that taught me that it's actually quite impossible to project yourself into someone else's brain.
Listening to the stories about the strange minds of murderers, he became obsessed with how someone's brain could create a reality so different from his own. But the problem was, science class left him cold.
Unfortunately, I didn't like high school science that much. There's always the answer in the back of the book, and what you're trying to do is get yourself through something that other people have already invented.
At Rice University, David majored in literature, but while he was supposed to be reading the classics, he found himself wandering into a different part of the stacks, the neuroscience section.
And it never struck me that I might actually go into a career in neuroscience until a friend of mine suggested that. He said, well, why don't you become a neuroscientist? Why don't you study the brain as your career? And it just felt like, oh yeah, of course.
After receiving his PhD from the Baylor College of Medicine, he opened his own guerrilla-style lab where he looked for unique ways to show how the brain creates reality. That's when he started reading about a peculiar condition that had never been systematically studied, synesthesia.
I just view synesthesia as a different way of perceiving the world,
where people blend unrelated senses.
A's are always red, and M's are green.
So their letters and numbers have colors.
0 is white, 1 is black, 2 is kind of a light pink color.
2 is fuchsia.
Or they feel music as if it's floating around them.
I would feel things, I guess, starting from below me and behind me, spiraling up, going through this piano range, and then ending somewhere in the corner.
When I used to do spelling bees, it was really easy for me to reproduce the spelling of the word based on the colors I would see. And when I was in 8th grade, I got second in the Texas spelling bee.
Applause. A-P-P-L-A-U-S-E.
Most of the papers in the literature just had a single subject in it. They would say, we have found a synesthete and here are her characteristics. So I thought, is there a way that we could actually get thousands of synesthetes? And so I turned to the internet.
David designed an online test to verify that someone has synesthesia, and it spread virally.
So at this point, I've interviewed and rigorously verified and have all the data on over 6,000 synesthetes. And that has really changed the field.
He now had a huge pool of subjects he could study with the latest scientific tools.
So it turned out that one of our synesthetes was getting married.
David saw a guerrilla science opportunity. The family would all be at the wedding, but what he really wanted was their DNA.
We crashed a wedding where a whole bunch of people were coming together from the family. And we showed up, and we had everybody spit in the spit kit. Then we left. And that was a great way to get a lot of data at once.
Next, he wanted to look inside the heads of synesthetes to see just how their brains worked.
We take someone with synesthesia, they go inside the fMRI machine, then we show them a video from Sesame Street. And we've turned it into grayscale, so there's no color involved. But there are lots of letters and numbers flying at them.
The fMRI gives David a map of what parts of their brain are active. When the synesthetes watched the video, they saw something very different from the rest of us.
Even though the cartoon was in black and white, I perceived the number as being in color.
So what clues did he find in the fMRI images?
What we seem to be finding is that the areas involved in letters and numbers are right next to the areas involved in colors and textures and spatial forms.
What David saw supports the idea of a kind of crosstalk between two adjacent but unrelated parts of the brain.
It appears that in synesthesia, there's just a slight tweak on that. Activity in some area will actually excite activity in a neighboring area. So this has led us to a new anatomical understanding of what's happening in synesthesia.
With each new experiment, David understands more about how the tiniest changes in our brain profoundly shape our realities.
It turns out that people's realities can be quite different.
David's own brain has helped him forge a unique path full of triumphs and failures that is changing how we view our most vital of organs.
Brains are like fingerprints, and they're slightly different in everybody. So being inside my head and being inside someone else's head can be very different.
And studying such unusual brains has helped him understand just how different our realities can be.
We're different on so many levels. Even just the way that we see the world is different from one person to the next.
I don't know what it would be like to have letters and numbers that didn't have colors. Like, that seems like it would be such a dull and drab way to experience them.
Ba, ba, ba. ba, ba, ba. Ba, ba, ba. Ba, ba, ba.
Ga, ga, ga. Ga, ga, ga. Ba, ba, ba.
And now for some final thoughts on how our brain works. We praise our brain in many ways, but that's surely because it's our brain. But we're so easily fooled by other humans and even by nature itself that we need the methods and tools of science to shield us from bias, blunder, and even delusion. If we were honest with ourselves, then, for example, books on optical illusions would really be called brain failures. The human brain may linger as the last thing in the universe we ever completely figure out. Apart from the philosophical challenge of a mind coming to understand itself, the extreme case of an experimenter interfering with the experiment, there's also the ethical challenge of how you come to know what goes on inside a living person's head. Normally, when confronted with a mysterious orb, an experimentalist pries it open, slices it, dices it, analyzes it, chemically, physically, and biologically. Problem is, people don't normally volunteer their living brains for such studies. Our best hope today lies with the neuroscientists. What are thoughts but electrical impulses among brain cells? What are ideas but novel firings of those cells? What are mental problems, if not impulses that have misfired? In the way that chemistry arose from the ashes of alchemy, neuroscience, a field still in its infancy, may one day subsume psychology, laying bare our inner universe, which has remained hidden for so long. And that is the cosmic perspective. And now we'd like to hear your perspective on this episode of Nova Science Now. Log on to our website and tell us what you think. You can watch any of these stories again, download additional audio and video, explore interactives, hear from experts, and watch revealing profiles from our web-only series, The Secret Life of Scientists and Engineers. Find it all at pbs.org. That's our show. We'll see you next time.
Next time on Nova Science Now.
How smart are animals?
Very smart. Dolphins problem solving.
He outsmarted me.
Good! Dogs acing tests our closest relatives can't pass. And you won't believe what she can do.
There's 1,000 toys here. She knows the name of every single one of these.
Parlor trick or true intelligence?
How many? What? We were communicating with another species. It was the Dr. Dolittle moment.
Next time on Nova Science Now.
Funding for Nova Science Now is provided by the National Science Foundation, where discoveries begin. And
discovering new knowledge. Biomedical research and science education. Howard Hughes Medical Institute. HHMI.
and the Alfred P. Sloan Foundation to enhance public understanding of science and technology.